Okay, can you hear me? Yes. So, good morning, everybody. So today I'm going to talk about BGP, BGP monitoring, RPKI Route, ASPA, BMP, so quite a lot of exciting topics. So let's get started. So probably many of you know BGP. It's the main inter-domain routing protocol used today. And with BGP, it's critical that we get data from actual BGP routers, such that then we can use this data to build monitoring tools, such as Kaida's IceRank, BGPlay from RIPE. Also, there are some commercial services that use the data, and perhaps you're using these tools every day. And historically, there are 3 platforms that collect BGP data from actual BGP routers. It's RIPE RIS, RouteViews, PCH. So for instance, RIS and RouteViews, they collect and store data from about 1,500 BGP routers, which we also called vantage points. So today, I am here to present you a new BGP data collection platform, which is called BGP Routes.io. It's a new platform because we just launched it about 1.5 years ago. And perhaps you wonder, why did we decide to build this new platform when there are already RIPE RIS and RouteViews that exist and that work very well? Well, it's because when one wants to operate such a platform, there are typically 2 main objectives. We want to have a high coverage, so we want to get as much data as possible, because more data means more accurate monitoring tools. But in the meantime, we also want to keep the data for as long as possible, because, for instance, researchers, they love to go back in the past and do some analysis. The problem, though, is that these 2 objectives, they are not easily compatible. High coverage means that we want more data, but keeping this data forever, then it's more expensive. So typically what happens is that we need to prioritize. And RIS and RouteViews, what they do, they really want to put high priority into keeping the data forever. So that's amazing, because now we can really go back decades ago and measure what happened like decades ago. But recently, the price to pay was that they switched from open peering policy to a more selective peering policy, meaning not everyone anymore can peer with these platforms, especially if you are a hobby network, or if you bring a redundant feed, you might not be able to peer with these platforms anymore. So with BGP Routes.io, we want to do it the other way around. So we really want to put high priority into coverage. So we want to get as much data as possible. We have an open peering policy. Everyone is welcome to connect with us and share data, even if you're a hobby network, even if you operate an IXP. You are welcome to connect with us. The price to pay, though, here is that we will not keep the data forever. We will just keep it for a few months, and then eventually, when we don't have the resources to keep it, we just discard it. Okay, so now we also say that BGP Routes.io is a next generation BGP route collection platform, and I'm going to explain you why we say this. And first, let's start with the new strategies that we are using to enable high coverage. So we rely on 3 key ingredients here. And the first ingredient is automated peering establishment. So if you're in this room and you would like to contribute data, there is nothing easier than that. You can just go on our website, you can authenticate with your PeeringDB account, and then you just have to fill up a very simple form. It takes 2 minutes, you submit the form, you configure BGP in your router, and that's it. And then you will start sharing the data with the community. So thanks to this, today BGP Routes.io collects data from about 100 networks. This is already good, and especially also because this number is always increasing every week. And the problem, though, is that it's still not sufficient, right? I mean, we all know the number of ISEs on the internet is like 80K, something like this. So it's way more than 100 networks. So it's still insufficient, and we still need many more networks that contribute data. And this is why we have the second key ingredient, which is data aggregation. So here we don't just take the data from our own peers, but we also take all the data that is available in public repositories, typically from RIPE RIS, RouteViews, PCH, and CGTF. CGTF is also a small data collection platform in Asia. So we take all this data and we centralize it into one single database. So if you go on our website, you can really see all these vantage points. You can see from which platform they actually come from, and then you can navigate through them. So with this aggregation, BGP Routes.io stores data for about 5,000 vantage points when everything works well. And this is a map which is called the choropleth map. And basically here, greener is a country, higher is the number of vantage points in that country. And you can see that there are quite some countries that have a lot of vantage points, especially in Europe and in North America, for instance. So this is good, but there are also many countries which lack vantage points, like there is no vantage points at all, for instance. So typically in these regions, maybe the monitoring tools, they are not so accurate. In Switzerland, we count about 111 vantage points, 19 connected to BGP Routes.io, 89 to RIS, and 3 to RouteViews. This is good. But in Switzerland, there are also many networks. There are, I think, more than 1,000 networks. So if we take the proportion, it's still a tiny fraction of them that actually contribute data. So this is why I'm here today, is to try to convince more of you to share data with one of these platforms. OK, so the third ingredient now is BMP. So why BMP helps here? It's because when we want to use BGP to monitor BGP, we are typically wasting information. Why? Because BGP only exports the best and non-filtered routes. That's how BGP works. And so we are really wasting a lot of useful information. And let's take a little example here. Assume we are IS-123 and we have two providers which both announce a full routing table, so about 1.4 million routes today. And then you also assume that IS-123 is connected to an IXP, through which it has some bilateral session, for instance, with peer 1, or it is also connected to the route server. So this is a very typical setup. And then we can look at the RIB of IS-123. So in this case, the RIB, for instance, contains about 3 million routes. But if we now imagine that IS-123 connects to BGP Routes.io with a BGP session, it is only going to announce 1.4 million routes, the best routes. And all the others will not be announced over the BGP session. So typically here, the iceberg analogy that we all know works pretty well. The route collected from a BGP session are just the top of the iceberg, and most actually remain invisible. It's the bottom of the iceberg. Is that actually bad? Yes, it's not so good, because in these invisible parts, there might be critical events such as route hijacks, zombie routes, route leaks, you name it. So BMP can help here. Why? Because first of all, it can export all route updates received from every peer of the router. And that means also backup routes will be exported. And second, because BMP can also export route updates at all stages of the BGP processing pipeline, including, for instance, in the pre-filter stage. So even the routes that are filtered can be exported through BMP. So for instance, this is even better than if you would use BGP at pass. And finally, it's also very simple to configure. It's just a few lines of configuration in your router, and that's it. So now if we take our previous example, and we assume that IS-123 configures a BMP session with BGP Routes.io, well, then IS-123 simply exports all the 3 million routes. So we will really see everything here. OK, so today, BGP Routes.io has about 39 BMP sessions with 19 different networks. And the previous example I just illustrated before, it's not just like a theoretical example. It's really an example that we can find in the real life. For instance, EdgeConnect, IS-328.365 from South Africa is connected to BGP Routes.io with BMP. And through that BMP session, it literally exports routes from 465 peers. So this is quite a lot of data from just one single BMP session. And for instance, it brings an IPv6 full feed from Hurricane Electric. It brings a few feeds from IXP route servers, so for instance, the NAP Africa and the ANX ZA route servers. And it also brings feeds from hundreds of bilateral sessions that it has through these IXPs. So this is quite a lot of data, a lot of useful data. We have some dashboards actually available online, and you can really see these networks that are connected with BMP. EdgeConnect is really like the first one with more than 400 peers. But we also have other networks just below which are connected with BMP and which export data for more than 100 peers. So again, this is quite a lot of data. If you're interested, you can even click here and you can really see the peers connected to EdgeConnect from which we can get the data. For instance, one of these peers is the ANX ZA route server. Another one is the NAP Africa route server. And then you can even click there and really navigate through the raw data if you're interested. What about Switzerland? Well, good news, we have a network in Switzerland that is connected to us with BMP. It's a canton of Appenzell-Ausserrhoden. So you can actually visualize it here. It brings data for 16 peers. And amongst them, we get data for Rheintal IX, Init 7, a Swiss IX. So this is very useful data as well. OK, so now I'm going to talk a little bit about BGP security, because I guess we all care about that. So let's see. So when we receive a route with BGP routes.io, we immediately tag the route with its RPKI, LOV, and ASPA status, inferred at the time the route is received. So in the case of LOV, it's quite simple. LOV, it's a mechanism that assesses whether the origin in the ASPAs can announce the prefix. So here the outcome is valid, invalid, unknown. So we just tag the routes with valid, invalid, unknown. And ASPA, it's a new mechanism that aims to check whether an ASPA has a value-free violation or not. So this could typically help to detect route leaks or forged ASPAs, for instance. And here it's a little bit more complicated. I cannot really go into the detail of ASPA. I don't have the time. But basically in ASPA, there are two algorithms. There is one for upstream ASPAs. These ASPAs are the paths we received from a customer, a peer, or a route server. And they are downstream ASPAs, which we receive from a provider. And depending on the two cases, we need to use two different algorithms. So the problem here with BGP routes.io is that we don't have peers, customer, provider. We just have contributors. So we don't really know which algorithm we should use. So what we do, we just run the two algorithms, and then we tag each route with the two outputs. So that means a route is tagged with upstream valid, invalid, unknown, and downstream valid or invalid or unknown. So, OK. So that's for the security part. But then we have also a set of APIs and dashboards that you can use to analyze all this data. And this actually matters because collecting more data, tagging it with some information, it's not so useful if users they are not equipped with the tools to effectively analyze this data. So you probably know the MRT archives from RIPE RIS and RouteViews. And in these archives, there are tons of MRT files. And in these files, everything is mixed up for different prefixes, different aliases, and then it's compressed. So to analyze all of this, it can be quite complicated, quite hard, time-consuming as well. So yes, with BGP routes.io, we do have an MRT archive, but we actually recommend to use the API instead. So we have built this API to be simple and fast, and also so that it can provide a high granularity access to the BGP data. So you don't need to use MRT files anymore. You can just use this API instead. It's much better for most of the use cases. So the API offers 4 endpoints, vantage points, updates RIP topology. So depending on what you want to do, you can use one of these endpoints. And each endpoint comes with a set of parameters. So the goal is really you can build very flexible queries, so you don't have to download irrelevant data anymore, but you can just get the slice of the data that matters for your experiments, so it will make everything much faster. Imagine, for instance, you're a network operator and you want to get all the BGP updates for which your ISN appears in the ASPA today. So what you can do, you can use our Python client, which is called PyBGP Routes API, and you import the vantage points and the updates functions. And then you use the vantage points function to get the vantage points that you want, for instance, all the ones from BGP routes.io and RIPE RIS. And then you just have to iterate over these vantage points, and then for each of them, you call the updates function, you specify a time frame, and then you can use ASPA's regular expression to just get the updates for which your ISN is in the ASPA. Okay, and if you do this, you will maybe just get 4 updates. That's it. These 4 updates where IS3, for instance, appears in the ASPA. And so it will make everything faster because you just have to process these 4 updates. As I was saying before, we also tag each route with the LOV status and ASPA status, so you can see them here. And now with this information, what's nice is that we can even filter the routes based on their LOV and ASPA statuses. For instance, when we use the API, we can even use the LOV status and ASPA status parameter. So for instance, here we can say, okay, I just want the updates for which the LOV status is valid or unknown, and the ASPA status is down invalid or down unknown. And if you do this, then you will just get the first and the last updates because they do match these criteria, but you will not get the 2 updates in the middle because they do not match these criteria. So thanks to this, now you can do measurement studies, for instance, and you can try to measure, for instance, the deployment of ASPA. And this is what we did. We actually analyzed ASPA for downstream ASPAs. And for that, we used all the updates that we collected within a 2-hour time frame. And what we found is that 99.3% of the routes, they are downstream unknown. And that is expected because there are not so many ASPA objects so far, so most of the routes, we just don't know if they are ASPA valid or invalid. But we found that 0.04% of the routes are ASPA downstream invalid. And this is quite interesting because these routes, they are typically route leaks, probably. It's just 0.04%, but it represents hundreds of routes, actually. And finally, we also found that 0.7% are valid. So this is good news. There are already valid ASPAs out there. So that's a good news. And we can hope that this number increases over time. As I was saying, we also have a set of dashboards online. So if you're interested, you can look at them. I'm not going to show them now. I don't have the time. But if you're interested, you can definitely go on the website. And that's it. So thank you very much. If you're interested, feel free to connect with us. All the data is publicly available. And also thank you to our sponsors, the APNIC Foundation and OVH Cloud. Thank you.
Do we have any questions? Oh, I see one in the corner there. The hard ones to reach.
Hi, Sylvan from 58299. I have 1 or 2 questions to this. First of all, is it possible that this also would be mobile capable, would be appreciated? It does not work on a mobile phone, I just tested.
Yeah. So maybe one day we will do a sort of a phone application. I definitely agree. It is on the to-do list. It's just that we are just working on this, so we have a lot of things to do. But it's definitely on the to-do list. Yes.
Then the next thing, can you go into detail what this inferencing works? Because it keeps, if you click on the button inference, it keeps disagreeing immediately with the dataset underneath. It first says that my upstream, zero path has been found that this is my upstream and I'm completely their upstream. And then it shows the complete opposite of those data in your website. So it disagrees with itself on the website. So what is this inference? Is this a machine learning thing?
Yeah, so you mean so if you go, there is a dashboard that is called the AS Explorer, right? You refer to that dashboard, I guess, right?
Yes.
Okay. And in that dashboard, we show, the upstreams, the downstream, and the peers that we can infer from the BGP data. We are using a probabilistic inference, which is rather basic. We are actually describing the inference if you click on the documentation button on the top right corner, you can see how the algorithm actually works. And the problem is that sometimes this algorithm can make mistake, and we acknowledge this on the documentation. Sometimes it's actually operators that, it's not operators, they are route leaks sometimes, and then it can make an incorrect inference because it is a route leak, not because the algorithm did something wrong. So so it can be, I agree, sometimes, let's say, suspicious, but it's actually often useful for operators to investigate because, we already had several cases where we talked with the operators and they were like, oh, this doesn't look good. And when we investigated with them and we actually realized that it was due to route leaks, for instance. Now, I think what you are referring is the description of why we did this inference more precisely. And then I'm not so sure why you see something that is not consistent with the other page. I would be happy to discuss this with you because we are working on trying to make things pretty clear. That's the general thing. So let's talk more. Maybe there is a bug somewhere. Let's chat more. I'm very happy about that. Definitely. Yeah.
And the last question is, can you also show detail why my upstream are suddenly a violation? Would be a nice feature request, because it says violation on my upstreams, which are legit.
Violation for the IRR or?
Yes.
Yes, for the IRR. So we have another dashboard. I can show you later. We have a dashboard that is called the IRR Explorer. And if you go in that dashboard, then you have the connectivity tab. If you go in the connectivity tab, we explain why we make these inferences. It's from the outNum object in the IRR. We try to infer. Again, it's probabilistic. It's probabilistic, so we can make mistakes. That's definitely possible. But that's basically how we do it.
Okay, one last question.
Thank you. This is Severin from Ost University. Very nice work. I also said it to your colleagues on a former meetup. My question is related to BMP, especially the BMP collection pipeline. Could you share some insights in how you do the collection? Because we explored it's not so easy to collect BMP, especially in real time, if you have like huge amount of data.
Yes, well, that's a good question. This is actually what takes most of our time. It's not really building dashboards and all these things. It's collecting all this data. BMP is rather new, so even though there is an RFC, every vendors implement it with its own flavor. So we spend a lot of time debugging things, trying to make sure our code works with all the vendors and everything. Then once it works, indeed, we had to work quite hard on designing a database scheme that can, handle all this data. So we have our own collector. It's C code, so it's optimized. So we can run it on like commodity servers and handle all this data on just one commodity server. But yeah, so this is really something we have been working on for quite some time. Actually, some of our research papers, they try to address this issue of like the volume of data. How do we address this, and especially how do we, manage this trade-off between volume of data, but also being fast at answering queries, because storing data, it's easy, but in the meantime, if you want to get quick answer when you do the query, this is fast, right? This thing. So this is really where we put most of our effort today. Yeah.
Okay, thank you very much.
Thank you.